Today in this video I'm going to show you how to use the trigonometric identities that we've been working on recently and use these to solve trigonometric equations. So let's just talk about one of the trigonometric identities that we've looked at recently. This sine squared theta plus cos squared theta equals 1. And of course this can be rearranged so that we can have either sine squared theta is the subject or cos squared theta as the subject. So if I was to just make cos squared theta the subject, for example, that's going to be 1 minus sine squared theta. And likewise, if I make sine squared theta the subject, sine squared theta becomes 1 minus cos squared theta. And we're going to use this along with possibly other trig identities such as sine theta over cos theta equals tan theta. Okay, so I have just scrubbed out some room and I've written a question up. So what we're going to do is we're going to solve this equation here. We've got 2 sine squared x equals cos x plus 1, and we're solving within the domain 0 to 2 pi. So the first thing I've got to do is identify that this equation has both sine squared or sine x, a function of sine x, and cos x within. And at the moment we only need to turn that into, or we only know how to solve equations that are in terms of either sine or cos. So we're going to rewrite sine squared x using one of these rearrangements of this identity here. I'm going to make the sine squared x equal to 1 minus cos squared x. So let's do that first. And I'm going to try and write down here and down here because it's quite a lot of work in here. So let's replace sine squared x for 1 minus cos squared x in there. And then we keep writing the equation equals cos x plus 1. Okay, so the first thing I'm going to do is expand the brackets. So we're expanding the brackets. I'm going to try and move out of the way because I've chosen blue and I'm wearing a blue dress. So multiply that out, you get 2 minus 2 cos squared x equals cos x plus 1. The next step is to try and get everything over onto one side because we've got a squared term here, a power 1 and a constant. So when I move it all over to one side, it's going to be a quadratic equation. So moving this over gives me 2 cos squared x. I've still got this here, so it's plus cos x plus 1. And then I've got to take the 2 over as well, so take away 2. So let's just neaten that up a bit. I've got 1 take away 2, which is minus 1. So you can either factorize this as a quadratic using cos x as your variable, or you can do a substitution. I like to do a substitution, it just makes it a little bit simpler. Let's let cos x equal y. So if I rewrite this, I now get 0 equals 2y squared plus y minus 1, which is much easier to work with and not as clustered. Okay, so factorizing this then. Well, when we factorize this, we know that it's going to go into a bracket, so we get, hang on, wait a second, I've got to have a 2y there, 2y minus 1 and y plus 1. And of course, if you aren't sure how to factorize this quadratic, don't forget to check back on factorizing quadratics video. So now we can substitute our original cos x back in. We get 0 equals 2 cos x minus 1 multiplied by cos x plus 1. As you can see, we can use the null factor law to solve this because we have 2 brackets and it's equal to 0. So solving that gives me 2 equations that I need to look at. Either 2 cos x minus 1 equals 0 or cos x plus 1 equals 0. So let's solve each of these individually. Let's just focus on this one first. Moving the 1 over, we get 2 cos x equals 1. Dividing by the 2, you get cos x equals 1/2. Now you should look at that and go, that's an exact value from a special triangle. So we'll hang on to that one for a second. Let's just look at this one over here. Cos x equals -1. Now, if you think about that, let me just move that out of the way, it might be a bit clearer. If you think about that, that's a boundary angle. So you can look on your unit circle. Now, the key things here is we've got a domain that we're trying to solve within. So we're only interested in those values between 0 and 2 pi. So that's one rotation around the unit circle. Cos x is positive here, and cos x is negative here. All right, so I've just cleared some room and I've drawn the special triangle in the question. So looking at cos of the angle is to do with adjacent over hypotenuse. So if I draw a special triangle here and we look at a triangle that's got the adjacent as 1 and the hypotenuse as 2, we've got 60 degrees, which, because we're in radians, we want pi over 3. So our acute angle is pi over 3. Now we have to work out if that's actually a solution. So we think about it, we're looking at this domain, let's draw our unit circle. We're dealing with positive values where cos is positive. Cos is positive in the first quadrant. So therefore, pi upon 3 is our first solution. So I'm going to call that x1. Now let's have a look to see if there are any more solutions within this unit circle here. Yes, there is another area where cos is positive. So what I need to do is work out what 2 pi minus pi upon 3 is to get my second solution. And working that out, obviously you can turn that into 6 pi over 3. Take 1 pi over 3 is 5 pi over 3. So our second solution is 5 pi over 3. Now let's go to this second equation that was created. Boundary angle. Well, cos x is to do with the x-coordinate on the unit circle. Where on the unit circle is the x-coordinate -1? It's over here. And so this coordinate, remember, is -1, 0. So this angle here is pi. So our third solution, which is generated from that second equation, is pi. So there are now 3 solutions within this domain of this equation. They are pi over 3, 5 pi over 3, and pi.